the moving charges, 2 marks, 3 marks questions of moving charges chapter. Okay. Okay, fine. So we will start with the 29th question. Okay. So from 29th, it's question based upon the chapter moving charges. Okay. So what it's been given there, write the expression for magnitude of force on a charge moving in a uniform magnetic field. Explain the terms. Okay, it has been said that write the expression for magnitude of force on a charge moving in a uniform magnetic field. So as you know that whenever a charge which is moving in the presence of magnetic field, okay, so it experiences a magnetic force. Okay, so we have already derived it. So the expression for that comes out to be as F is equal to qvb sin theta or bqv sin theta. Okay, so where F represents the force experienced, B is nothing but it is a magnetic field, V is velocity of charge, Q is magnitude of charge, and theta is the angle between V and B. Okay, so the next thing is, when does the force experienced by a charged particle moving in a magnetic field is minimum and maximum. Okay, so we need to find in which direction, okay, or when is the force experienced by a charged particle moving in the presence of magnetic field experiences maximum force and minimum force. So as you know that the charge experiences the maximum force in the presence of magnetic field when it is moving perpendicular to the direction of magnetic field, that is when theta is equal to 90 degree. Okay, so that is when the angle between V and B is 90. Okay, at that point, I mean at that case the force is maximum. Okay, the minimum is when the charge is moving parallel or anti-parallel. Okay, here it has been given only parallel, so even it is true for anti-parallel. Okay, so that means that when the charged particle is moving along the direction of magnetic field or opposite to the direction of magnetic field, the force experience will be a zero, because sine 0 and sine 180 is nothing but equal to 0, right? So hence the force will be minimum when the charged particle is moving parallel or anti-parallel. Okay, so that is regarding the 30th question. So the next one is, it is regarding the cyclotron. So cyclotron has been removed from the syllabus. Okay, don't worry, I mean for this year they have removed. So we will go to the next question, that is 32nd. Okay, and one more thing, while you are getting prepared for this midterm examination, please go through that syllabus, the which is that 30% reduced syllabus which has been released by the PU board. I think you have in your group, right? Just go through whichever the topics has been removed. Okay, so leave that topic from this I mean in this file. Just don't go through that questions. Okay, apart from that, go through the rest of the uh, questions. So the next is nothing but write the Biot-Savart's law and explain the symbols. So it is said that the magnitude of the magnetic field at any point due to a current element is, okay. So why do we use this Biot-Savart law? First of all, to find the magnetic field, okay, to find the magnitude of magnetic field at a given point due to the current element. So suppose let us say that this is my conductor. Okay, let us consider this as a current carrying conductor. So I need to find the magnetic field at this point. Okay, so what I'm going to do is I'll consider a small element. Okay, so I'll consider a small current element of this and I'll find what is the magnetic field at this point due to this small element. Okay, so then we will find by writing a position vector. Okay, by drawing a position vector, so it makes an angle of theta. So then we will we are going to find the magnitude of magnetic field at this point. Okay, so this magnitude of magnetic field depends upon, first of all, it depends upon the strength of the current, which is directly proportional to the strength of the current. Okay, the first one is directly proportional to the, okay, first one, it depends upon the directly proportional to the strength of the current. Okay, so if the current flowing through the conductor is more, so obviously the magnetic field at this point will be more itself. Okay, so next is nothing but directly proportional to the length of the current element. Okay, directly proportional to the current element. Okay, it means that if you consider the current element, okay, so I said that we have considered a small element, right? If you consider a small element, the magnetic field produced at this point will be small itself. If you consider greater current element, okay, more, so what happens, the magnitude of magnetic field at this point will be more. Okay, it depends upon the current element also. If you take a small current element, small magnetic field, more current element, greater the current element, greater will be the magnetic field. So hence they have written that dB is proportional to I, dB is proportional to dl. Okay, dB is nothing but magnetic field at this point. Okay, dB. So next it is said that directly proportional to the angle between the current element and the line joining the point from the current element. Okay, so see here, as you know that in the figure you can see this is the P is a point where we need to find the magnetic field. Okay, and R is the position vector. Okay, and you can see there it makes an angle of the current, the conductor makes an angle of theta with respect to the uh, point P. Okay, so hence we say that dB is proportional to sine theta. Okay, why only we take sine theta, why not cos? Okay, so just think about that. So once we are done with this, you can give the answer. Okay, so dB is proportional to sine theta. Next is dB is inversely proportional to 1 by r square. That means that it obeys the inverse square law. Okay, as you go away from the conductor, suppose the point where I have taken here, instead of this, if I take here at this point, so obviously the distance is more, so hence the magnetic field varies inversely with the distance. Okay, so as you go away from as you go far from the conductor, the magnetic field also decreases. How it decreases? Decreases by 1 by r square, inverse square law. Okay, so clubbing all those points which we just gone through, so you are going to write dB is proportional to ideal sine theta divided by r square. Okay, so it is a proportionality, okay, term. So in order to replace that with equal sign, what we are going to do, we need to add a constant. Okay, that is k. K is nothing but equal to mu naught by 4 pi. Okay, so hence you can write dB as dB is equal to mu naught divided by 4 pi into ideal sine theta divided by r square. Okay, so this is regarding the Biot-Savart law. Okay, so just go through this Biot-Savart law once, and the question which we gone from 29th question, just go through once till Biot-Savart law. In case if you have any doubts, you can ask. Okay, fine students, any doubts? Shall we move to the next? In case if you have any doubts, you can ask. Okay, fine. So we'll move to the next now. That is 33rd question. State and explain Ampere's circuital law. Okay. So coming to this Ampere's circuital law, it is said that the line integral of magnetic field around a closed path or boundary, that is closed integral of vector b dot vector dl, is equal to the mu naught times the total current I through the surface that enclosed by path or boundary. Okay, so see here, you can take the reference of this figure itself here, which you have. Okay, so as you know that when you have a straight conductor, okay, when you have a conductor which is straight, so as you know that the magnetic field produced will be in a form of loop, right? So you can see there in the figure you have a conductor, okay, and the magnetic field produced will be, it is a it is in the form of loop. Okay, so now in order to find the magnetic field around any closed path, okay, loop is a closed path, right? In order to find the magnetic field at any point on that, so we are going to express that as, which is equal to mu naught times the total current passing through that loop. Okay, so that means that mu naught is nothing but what it is, permeability of free space, because the gap between the loop and the straight wire, that is the conductor, is nothing but it is a free space, right? That is vacuum or air. So mu naught into current which is flowing through the conductor, we say. Okay, amount of current flowing through the conductor. So hence we are going to express the Ampere circuital law in mathematical form as closed integral vector b dot vector dl is equal to mu naught into I. Okay, so this is the mathematical form of Ampere's circuital law. Okay, okay, so this is regarding the Ampere circuital law. So next we will go through with the solenoid. Okay, so first of all, what is solenoid? Anyone? What is solenoid? Where you are going to take a cylindrical core. On that cylindrical core, where you are going to wound the wire, so that itself is called as the solenoid. Okay, okay, Nikhil. So when you take a cylindrical core and where you are going to wound the copper wire on that, that itself is called as a solenoid. So next it is said that write the expression for magnetic field inside the current carrying solenoid. Okay, so the definition is for what is solenoid is a long insulated copper wire wound closely in the form of a helix. Okay, so where you are going to take an cylindrical object, on that cylindrical object where you are going to wound the insulated copper wire, so that what you have wound, that copper wire should be wound very closely in the form of helix. Okay, so that itself is called as the solenoid. So next, the expression for magnetic field inside the current carrying solenoid comes out to be as B is equal to mu naught Ni. Okay, so where N is the number of turns per unit length of the solenoid, and I is the current through the solenoid, and mu naught is the permeability of free space. Okay, so this is regarding the solenoid. Similarly, in the bracket they have given toroid is a ring shaped closed solenoid and the magnetic field inside the toroid is B is equal to mu naught Ni. Okay, what is toroid? Toroid is nothing but what you have the solenoid. If you that cylindrical object is made, okay, it is made, I mean, so that if that solenoid itself, if you are going to bend that solenoid in the form of the closed loop, that itself is called as the toroid. Okay, so hence the magnetic field inside the toroid also comes out to be the same. The expression comes out to be the same, that is B is equal to mu naught Ni. Okay, B is equal to mu naught Ni. So the next is derive an expression for magnetic field due to a straight conductor of infinite length carrying current using Ampere's circuital law. Okay, so even this is a important expression. Okay, with the ask for 3 marks. Okay, so we need to find expression for magnetic field due to a strong conductor of infinite length carrying a current. So as usual, the same figure. So we have taken a straight conductor. As you know that the current is flowing in the upward direction in the conductor. So the magnetic field produced will be in the form of circular loop. So let us consider R be the radius of this loop. Okay. So in order to find the magnetic field, okay, at any point on this loop, so what we are going to do is we will draw a, I mean, we will take a small current element. Okay, so we will take a small current element which is represented by dl vector. Okay, so when I take this current element, okay, when I take this current element, so in order to find what is the direction of magnetic field at this current element, so what I am going to do, how I am going to find the direction of magnetic field, just I am going to draw a tangent. Okay, and just I am going to draw a tangent. Okay, so this represents the, that is the tangent what we have drawn represents the direction of magnetic field, and dl is nothing but a, it is a current element. Okay, so now this is regarding the how we are going to find the magnetic field. So let us come to the theoretical part here. It is said that consider an infinite long straight wire xy carrying steady current I as shown in the figure. Let P be a point at a perpendicular distance r from the wire. Consider a circle of radius r around the wire passing through the point P as Amperian loop. Since every point on the loop is at the same distance from the wire, the magnetic field B is same at all points and parallel to the line element. So as you know that it is said that since the loop is at the same distance from the wire, okay, since we have drawn a loop, right, so whichever point you take on that loop, it is at the same distance. All the points what you take, it will be at the same distance from the wire. So hence what happens, the magnetic field remains the same at all the points, and wherever you take a current element, that is a small element dl, okay, so what happens? So the magnetic field will be parallel to the current element, whatever you are taken, wherever you are taken on that loop. Okay. So always the magnetic field will be parallel to the line element, that is the current element. So now applying the Ampere's circuital law for this closed integral of vector b dot vector dl is equal to mu naught I. So this is the standard equation. So now what we are going to do is vector b dot vector dl can be expressed as bdl cos theta, right? So since it is a dot product, right, so bdl cos theta, so theta is the angle between vector b and vector dl. Okay, b and dl. So as you know that we said that both the line element and the magnetic field are parallel to each other, right? So theta value comes out to be 0. Okay, so that since theta is equal to 0, cos 0 is nothing but equal to 1, right? So hence you can write that as closed integral of bdl is equal to mu naught I. So next what we are going to do, we will take out that b outside of integration. So that comes out to be as b closed integral of dl, that is nothing but equal to mu naught I. So next integration of dl. Okay, dl is nothing but what? Small element, right? Integration of that small element is nothing but adding up of that all the small elements what you have taken in this closed loop. Okay, so adding that all the current element, that is a small element what we have considered across that loop itself is nothing but we say that integration. Adding that itself is set as integration. So circumference of that loop comes out to be as 2 pi r, right? So hence we have replaced the dl by circumference of the loop, that is b into 2 pi r is equal to mu naught I. So b is equal to mu naught I divided by 2 pi r. So this is the expression for magnetic field due to a straight conductor of infinite length carrying current by making use of this Ampere's circuital law. Okay, which is important, which they keep asking for 3 marks. Just go through. In case if you have any doubts, you can ask. Okay, fine. We will move to the next. So the next is converting G to V and G to A. Okay. So just a minute. I'll just see whether it is there for whether it is there in the syllabus. Just I'll check out. Wait. Okay, we have this. So now see how do we convert a given galvanometer into ammeter? Okay, so first of all, let us go through how we are going to convert it. Galvanometer is converted into ammeter by connecting suitable low resistance, that is the shunt resistance, parallel to the galvanometer. Okay, so why do we use first of all this galvanometer? Galvanometer is used to detect a small current. Okay, why do we use this ammeter? Ammeter is nothing but which is used to detect the large current in the circuit. Okay, so now we need to we need to convert this galvanometer into ammeter. How do we convert? We convert it by connecting a suitable low resistance, okay, parallel to the galvanometer. So you can see in the figure here you have a galvanometer which is represented by G there. Okay, Ig is the current flowing through the galvanometer. Okay, so now what we have done is we have connected a circuit, I mean the shunt wire. Okay, so shunt wire or shunt resistance, okay, which has the low resistance, okay, which offers the low resistance. So we have connected, which is represented by S in the figure. Okay, so this is the shunt resistance we call. Okay, so now let us see what happens, how we are going to convert it. Okay, as you know that if more current flows through the galvanometer, what happens? The galvanometer gets damaged. Okay, so hence only a small amount of current should be passed through the galvanometer. Okay, where we are going to convert it that by, where we are going to convert that galvanometer into ammeter. Okay, so now see here what happens here is, let us consider that I is the current flowing here, okay, from terminal A. So what happens as soon as it enters this point here? Okay, so what happens, since we have connected the shunt resistance, okay, in parallel, so it offers the low resistance. Always the current flows in a path where the low resistance is offered. Okay, so in case if there is a high resistance, what happens, only a small amount of current flows through that. Okay, so hence since this shunt resistance offers a very low current, so what happens, maximum current flows through this path. Okay, only a few current, only a minute current flows through the galvanometer. Okay, so this is how you are going to convert a given galvanometer into ammeter by connecting a shunt resistance parallel to the galvanometer. Okay, so you can see here it has been explained there. 0 to I is the range of converted ammeter. Ig is the current required for full scale deflection of galvanometer. G is the resistance of galvanometer and S is the shunt resistance. Okay, so don't worry much about this. Okay, so this thing we are going to study in the practical. Okay, so the expression coming to this, okay, mathematically how we are going to write this, as you know that the potential difference across the shunt resistance is equal to potential difference across the galvanometer. Why is that equal? Since the galvanometer and shunt resistance is connected parallel, right? So in the parallel combination, always the potential difference remains the same, right? So hence the potential difference across the shunt resistance is equal to potential difference across the galvanometer. So hence potential difference is nothing but S into I minus Ig is equal to Ig into G. Okay, what is the current flowing through the shunt resistance? It is nothing but I minus Ig. I minus Ig is nothing but the current flowing through the shunt resistance. Okay, so hence we are going to write S is equal to Ig divided by I minus Ig into capital G. Okay, this is the expression. Okay, this is how we are going to convert a given galvanometer into an ammeter. Go through once. Okay, fine students, we have left out with 1 minute. Okay, the next one, converting a given galvanometer into voltmeter, we will discuss in the next class. Okay, so just go through these questions. As I said, just go through the topics which has been removed by the PU board. Okay, leaving that questions, go through the rest of the questions. Okay, so with this thing I am concluding today's class. We will continue the rest of the questions in the next class. Okay.